Okay, I want to welcome everybody to our third Hangout. This one's going to be all about CFD 2015, which was finally released last week. I've invited Heath Houghton, who's our product manager, to come and present for us. Might as well get it right from the source. Heath, go to the next slide for me. Okay, so first thing I wanted to do for everybody is just remind you, this is our third Hangout. We've had two previous Hangouts, one on results visualizations and the next one on handling some meshing errors. All these videos are posted to the YouTube channel under Autodesk Sim 360, and we hope to get them posted within 3 to 5 days. Okay. And where do we announce these Hangouts? Pretty much from the forums primarily, but we also announce under a Twitter handle, Facebook, LinkedIn, and a lot of you probably also get direct emails from our team. Next slide, Heath. There we go. So at this point, I'm going to hand it over to Heath. He's going to talk you through the rest of this Hangout. And bring your questions to us through the GoToWebinar interface, and Todd, myself, as well as Apollo and John Wild in Europe will be answering your questions, and we'll try to pass those on to Heath so he can answer them live as well. So at this point, I'm going to pass this on to Heath.
Thanks, Royce. I'm going to get off the slide pretty quick because I got ragged about, looked like I was at my first day of school in the picture by some of our team members, so I'll go ahead and get off that pretty quick. But yeah, so we're going to talk about Simulation CFD and what is CFD when it comes to 2015. What are the focus areas that we had? So from an agenda standpoint, just to give everybody an idea, I think I'll be talking probably for about 20 minutes, maybe 30. And then we'll just leave it up to open questions after that. I'm sure there might be a few that these topics bring up. But the main focus areas for 2015, if you look at big ticket items, are phase change simulation, extending the advanced mesh adaptation to other application areas, adding spatially variable boundary conditions mainly for our AEC customers. And there are other applications, but where we see it most is for our AEC type customers. And the report generator. So has been a big request off of the idea station. So a lot of the things you'll see were from idea station. If you guys put in stuff on there, we are listening. As a matter of fact, I need to go back in the next week or so and start updating some of those items and saying if we've addressed them or not. But then the heatsink model, so there's a new heatsink model that I'll talk about as well. Let's talk about phase change. So phase change is an extension or one piece of what I would call multi-phase. And if you look at current capabilities, when I say current 2014 capabilities, what we had was cavitation, humidity, steam, so the ability to be able to do basically superheated steam, and free surface. We also had some extensions of being able to do particle tracking and erosion, but those were, most of what we could do when it comes to multi-phase. For SimCFD in 2015, what we added was the ability to do liquid gas phase change simulation. So that means the ability to take boiling, the effect of going from a subcooled liquid to a saturated vapor all the way to superheated in one analysis, with boiling and take into account the different effects of thermal and flow that type of phase change would have. And we make it available for water, ammonia, R134A, other common refrigerants, but it's adaptable to where you can add your own custom blends if you have a refrigerant that we don't have in the stock database. So the target applications that we see are phase change, heat exchangers, and radiators. But basically anything where you have flow going through, it's, I wouldn't consider anything like natural convection. You're actually forcing flow, and you're using that refrigerant's high heat transfer capabilities while it's in a saturated vapor state to move heat off of a device. Those are the common applications. So think about, from an electronic standpoint, IGBTs or other high output electronics. You might have a cold plate and you run a a refrigerant through there, you're probably going to want it to stay in its saturated phase so that it can have a really high amount of heat removal. And that's really what this is designed for, is to show you that with an accurate depiction of heat transfer and pressure drop. So just another way to show what I just talked about, but what I like to say is that the physics are actually pretty complex. So we're actually taking into account the nucleate boiling that happens between the walls of passages. So there's some pretty sophisticated stuff going on, but it doesn't require a lot of knowledge from setup from the user. It's really just basically flipping a switch and making sure you put the right reference properties of the material. So what pressure is it operating at? So mesh adaptation, we included some new extensions. So we're adding free shear layers, compressible shocks, and heat-producing parts. We've had mesh adaptation since 2013, and I think that the way that the user should really look at what mesh adaptation is, it's an easy way to answer that age-old question, is my mesh good enough? Do I have enough mesh to be mesh independent? Is my answer, based on the inputs, is it independent of the mesh? And that's what mesh adaptation is really built for, is to get as accurate a solution as you can. And the only other uncertainties you have then are, are my material properties right? Do I have the, kind of the boundary conditions modeled correctly? The mesh should be kind of taken out of the equation at that point. So what does it look like? So for free shear layers on the left, I like to use simple representations, but on the left is just a pipe bend, and the transition from the red to the green is basically where the flow is separating and wanting to recirculate. On the right, after you go through mesh adaptation, you can see all the mesh concentrated and really capturing that separation really accurately without any user intervention. The software is doing it for you. And it's not just going to overmesh the entire model. So when I say mesh adaptation, it's going to add some mesh count, but it's going to add it where it's needed and not add it where it's not. And that's the whole goal of using a mesh adaptation. So again, there's that area where you see a real crisp location of elements in order to capture that separating behavior. So again, incompressible shocks is another other extension to this tool. And on the left, default mesh, you might not capture the shock very well. You might, but if you wanted to without that mesh adaptation, you're probably going to overmesh the entire model. And so here on the right, this is really fine detail of where the mesh is right at the shock layer. And we can see that it's not overmeshed for the rest of the model. So again, a way to get an efficient mesh that's mesh independent, and this would be more useful probably for external aerodynamics type of problems. So there's a quick video showing the solution progress as you go through the mesh adaptation. I'll probably just replay that guy just so you can get an idea. So kind of a default mesh, you get a general good view, go through one, then a couple of mesh adaptations, you get a real crisp shock wave there. So it also includes heat-producing parts. Hope this isn't misleading. It doesn't mean that it only adapts on heat-producing parts. Just if you have some kind of a heat introduction in the model, it will turn on this portion of mesh adaptation and give you, like you would see here, where there's high amounts of heat flux leaving a surface or high temperature gradients, put more mesh there so you know that your temperature gradients and heat flux removals on surfaces are going to be as accurate as they possibly can for the mesh. So next step is the spatially variable boundary conditions. So in the past, if you needed to have a varying velocity at an inlet, you basically had to subdivide that inlet. It's not a really efficient way of doing analysis, and users were letting us know that. And so the AEC industry in particular needed to say, okay, you know what, if I'm in an urban area or I'm in level country, this subdivision of that inlet or the way that velocity profile is going to need to be input is different. So we give now in 2015 the ability to match those physical measurements, those wind shear applications in a real simple interface. I mean, basically it's the same as putting in a regular velocity, but now you have a table of distance over the actual numbers and just give you a visual indicator of which direction that distance is going. Pretty simple. If you look at it from a result standpoint, here you can see this input, visually see what's going on here. It's obviously not constant. If you took a XY plot, for instance, you can see the variation that's occurring there. So a customizable report generator, again, was also asked for. If you're a long-time user of SimCFD back in the CF design days, you would have seen maybe an HTML version of report generator, and our feedback was people really weren't using it that much, and we changed some architecture and deprecated it. We got rid of it. Well, in the preceding years, we've had some requests, and the beginning, higher, I guess, raised hands, higher amount of raised hands saying, hey, we really do need a report generator. And the feedback we got was that it needed to be customizable, so that some guys might want a full-fledged report with all the setup, everything, basically a way to archive the way they run a model. And some people might just want it, just the decision center stuff. I don't want to copy and paste in a PowerPoint. Have it pull that stuff automatically. So we've made it customizable, where you can just pull whatever you want. It'll remember those options and puts it into Word. So puts it into Word, so it's shareable, it's printable. And here are just a couple of screen grabs. On this, you can see when you go to the report generator, which is right on the ribbon in the interface in the results section, it'll pop up this screen. What do you want to put in there for some of your introductory sections, and then what do you want to pick out that you want to put in the report? Is it some of the setup, all the setup? How many types of images do you want? And then which simulations or designs do you want to include, or analyses, scenarios? So here's just kind of what it might look like. It's all hyperlinked. I think it's pretty good, a very good implementation of what a report generator should be. I think we'll probably get a lot of feedback, because if the Idea Station kudos count was any indication, people will start using this pretty often. We'll get some feedback and make some improvements as we get even more feedback along the year. But that was the report generator. So this one's pretty big for me. If you look at electronics cooling, then one of the larger issues that users have had with electronics is that when they have a highly detailed heatsink like the one you see circled in blue, and they don't have just one, they have many, you start getting to a point where your mesh count gets so high in order to accurately capture that you might not have the hardware to run it. If you do, the run times are long. So what we've done is now take that heatsink that's circled and model it with a simple block like on the right to still get accurate flow results, accurate thermal results, but with much faster run times, much less mesh count requirements. That's what we've added in 2015. And do it in a way that's easy for the user to put his heatsink in. So common heatsinks that we saw that are needed are extruded pin, different types of pin-pin heatsinks, offset strip heatsinks. And if there's something that's not in our quick GUI that says, hey, what's the pin spacing and how thick are they and all that kind of stuff, if we don't have something that can accurately represent your heatsink, then the ability to put in manufacturer's tables. So on the manufacturer, typically have an output of your flow resistance and thermal resistance, and be able to put that directly in the interface regardless of heatsink configuration, and so you can accurately represent it with a simple block in CFD. The only thing you really have to put are, besides characterizing what the geometry would look like if you were to actually physically model it, is an approach surface and the base surface, so it knows where the chip is going to be located underneath it. So there are two options. I'll go through both of them on how to use this. One is quite simple, and if your chip is the same size as the heatsink, if that's the way you're modeling things, then model the entire heatsink as one block. That's one way to do it. I would say the more flexible way to use this new tool is to do it as two parts. So if you have one chip that's smaller or multiple chips underneath the heatsink, this is where you would use this second approach. So what you're basically doing is you model the base plate as a physical solid, and then wherever the fins are, you model that as the heatsink material. Still pretty simple to do, but I consider a two-part subassembly for each of your heat sinks. And this is the approach that I would actually recommend to almost everybody because of the flexibility that you'll have on further design changes and stuff like that if you want to add more chips underneath it or stuff like that. Again, so the setup, just to give you some screen grabs of what the setup looks like. It's an approach surface. The correlations for heat sinks, you have to tell it which direction the flow is going to enter into the heat sink. So if you have an extruded fin, you need to tell it, what is that face that the flow is going into, and then what is the base surface that it's going to be, pulling heat off of the chips or whatever physical devices. So it's a pretty simple setup. There's some added benefits to doing stuff like this. Any of our materials, you typically get more information from them, right? Some of the, if you're looking at fans, give you the fan curve. If you're looking at compact thermal models and electronics, you're going to get some information there. So here's what a tooltip when you're in the results will give you. It'll tell you, first of all, if it's operating within the bounds of what we would consider the correlations that are in the background doing the calculations, and then give you like whatever the thermal resistance is, how much heat you're removing with the heat sink. So quick understanding of how much heat is going out of the devices underneath, through the heat sink, and then what kind of air supply am I giving it? What's the temperature and velocity of the air that's approaching this heat sink? So I know if I'm starving the heat sink, for instance, or if it has a lot of heat coming off of other devices going through this heat sink, and you might want to change what your flow patterns are. So in 2015, I've gotten down through the list of the major things. There's a lot of other things, right? And I can't go into detail on all of them. A lot of them are based off of what I would call customer-focused improvements. Again, the idea station is an area where we grab a lot of information. But one of the big ones just kind of highlight consistent design, study bar, collapsing, and expanding behavior. So we worked pretty diligently on that. Out of things, added import options for different types of CAD. One of the big ones the two of the bigger ones that I've seen that I think people would be happy with are, the cloud and remote solving robustness. We work really diligently to make sure that if you send something to the cloud using our SimFlex products, what was considered Sim 360 Pro in the past, or naming-wise, that you always get back all of your results and there's no failed downloads. Regardless of your workflow, shutting down a computer or whatever, we went through tons of emulated workflows and really worked on that really diligently this last year. And then in addition, we're now fully one-way FSI with SimMechanical with a really easy workflow. So before last year, you could do thermal results, so you could do thermal stress, and now the pressures map over with the exact same workflow. Basically, you're in SimMechanical and you say, you know what, pull the Sim CFD result, and it happens automatically for you, and it's your new boundary conditions. If you need a lot briefer overview than what I just gave, what I would suggest is if you go to the Autodesk.com, I have a link here, there's actually like a 4-minute video of the overview of the new features. So if you need a refresher on what's coming out that's new, or you want to show somebody else, you could obviously go to our website, and there's a real quick, succinct video about the new big ticket items. Yeah, so I promised about 20 minutes. I think I might have kind of hit it on the head. So I'm really open for any discussion questions that you might have, and I might even open up the software to discuss anything that you want to look at. Okay.
Hey, Heath, you hear me?
No, I couldn't. I was waiting. I was about to start talking.
Yeah, so we had a good question that just came in. Why don't you talk more about the ability to have users input flow and pressure drop curves for the heatsink model.
Okay. Okay. Yeah. So the flow and pressure drop curves for the heatsink model. Yeah, that's a good idea. So let me get back to that part of my presentation and just share my screen again. So what we have the ability to do when it comes to the heat sinks is we have the ability to somebody can put in, if they have the most common type of heat sinks, like in our research, it was the micro channel, so the extruded fins, pin fins, whether it be inline or staggered, or even offset strip heat sinks. You can actually, in the GUI, just type in that type of a heat sink. And if you want to, if you have something that's different, like let's say you have an elliptical fin heat sink, which we don't have, in the GUI where you can type in all the parameters of what the elliptical fin heat sink is. You can go to the manufacturer of that heat sink, and they will have a flow resistance and a thermal resistance parameter. And you can input that directly into SimCFD in order to then have the proper flow and thermal characteristics that we're calculating with the with the geometry characterization that you would have in CFD. So I'll go ahead and pull open CFD. So let's say this is a heat sink. It's not, but let's say this is. If I were to actually look at the model itself, and you see one of the new types is heat sink. Go ahead and edit that. So again, when it comes to these guys, the type would be microchannel, right? So if I go to type, we would type in the thickness and all that. But if I don't want to go microchannel, I would just say heatsink profile, and I'm giving it the approach velocity and the thermal resistance that happens there. And in addition, the friction factor. And those are the most common ways that a manufacturer is going to communicate how their heatsink performs. Does that help?
Yep, I think that answers that question.
I'm seeing a few on chat. Are you guys? Should I just answer those directly, or do you want me to?
Yeah, if you see ones in there in the question feed, go ahead and directly answer those.
There's quite a few, so I'll try to. One of the questions on the phase change is, are there any type of blends for gasoline, for liquid to vapor transition? Oh, there's already answers on that. So that's already answered. I didn't notice the answers already being applied. You guys are quick, man. Yeah, the feed, you guys have rolled through it.
So Heath, this is a simple one you can talk about, but using mesh adaptation with manually specified mesh sizes.
Yeah, so when it comes to mesh adaptation, what it really does is it takes your default mesh, and it's easier to see. This could have been a manually defined mesh, right? It could be auto size, it could be manual, but what mesh adaptation is then going to do is then go ahead and adapt beyond that manually specified mesh size, right? So it's going to look at where it needs to be refined. Does that make sense?
Yep.
Yeah, there's I don't think a really a exclusion for that. The only exclusion that we have seen so far is that mesh adaptation doesn't occur in 2D right now. Other than that, I think that mesh adaptation is to the point now where we're in year 3 of mesh adaptation, and whatever your physics are, it should be able to give you that mesh independent answer that everybody really craves without having to be a meshing expert.
Heath, can we go back to the user interface and just show where you turn on mesh adaptation?
Absolutely.
Yeah, and just so everyone's aware, in terms of limitations of adaptation, it has become very robust in terms of what it supports, but it's only for steady-state simulations, and it doesn't support surface parts. So those are the 2 big limitations.
Yeah. Yeah, so surface parts, yeah. And again, we're going to be, extending these types of analyses to as we move on. But at this point, for I would say like the 90% of models that aren't transient, mesh adaptation is a great option, especially if you're a little curious, or if you have some really high velocity pressure gradients, recirculation, stuff like that. You want to make sure that that it's captured. So so if you look at your solve dialog, right, you have your control where you're telling it how many iterations to run and if you want to save stuff and what kind of physics. But you should go right over the next tab, adaptation. To enable adaptation, so I have surface parts in this, right? I can't do it. It's going to give you that warning. But for any other model, I have the ability to do adaptation. I can run as many cycles as I want. So in this case, 3 is the default. I wouldn't necessarily typically recommend going past 3. I don't see a lot of benefit after that. It nails it down so quickly that 3 typically is kind of the sweet spot. And the only other options are, save cycles. So what that means is, in my scenarios, if I don't save cycles, it'll just run it, remesh it based on the physics, the number of cycles that I want, and whatever is saved as the scenario that I started from, that's that final mesh. Now, if I want to compare, the default mesh to cycle 1, cycle 2, cycle 3, I'll just hit this, and it will add them in as separate scenarios in the decision center as they go. You can add coarsening, which is just another way to really minimize the impact on the mesh. It'll actually coarsen in areas that that you don't need more mesh, where there's hardly any physics actually occurring. And then there's advanced features, which we probably shouldn't dive into on this call, but you always hit the help or ask our support guys, if there's anything additional that you're doing that you might want to do there. Yeah.
This, I'm not actually quite sure, Heath. The IGES translator, I haven't really tried to use it yet in 2015. Does that support the automatically created volumes?
Yeah, so anything, it should, right? So anything that you have that's, with the new geometry import styles, it should automatically generate the fluid volume if it's a closed volume, right? So STEP, KTI, just all of them, it should do that. That's part of when we pull in geometry. If we can pull in that format of geometry, that happens in the background while it's being pulled in.
And I'm pretty sure we support this now. Compact thermal models with adaptation. That works, correct?
Yeah. So one of the big drawbacks we had in the past was if I'm doing electronics, now I have to start excluding some of my materials, right? The first year especially. And I think it was unfortunate because I think it made people kind of turn away from it, right? So if you had an electronics model, had a fan in there the first year, okay, can't run. Well, now for electronics, really the only exclusion, and then Royce was pretty much dead on, and I kind of showed it, was if I have a surface part, then it excludes the surface part from mesh adaptation. Now, I will say that you can typically get around surface parts pretty easily, and even in an electronics model, by just adjusting your compact thermal model to include that resistance as part of it. So. Does it make sense for me to show maybe some of the results that you would get out of phase change if anybody's interested? Has anybody asked any questions about that so far?
There was a couple of questions in there in phase change. I would definitely encourage it, yeah.
Okay. Yeah, so in this case, what I'm looking at is just to give you an idea of the model. This has like IGBTs kind of laid out, or high output devices, doesn't matter what they are, and a plate, and this is my surface part that I had in the model, that blue one, so I'll hide that, but this is the fluid path, right? So Flow comes in here. It's R134A, so it's actually a refrigerant. Flows through these channels and then goes out the other end. And if you were to just flow a liquid through here, you get pretty good heat transfer. If you flow a gas, not so good. But if you flow something that's actually in the saturated vapor state, really high heat transfer. And the setup's pretty simple. I kind of flew through the setup because I kind of anticipated getting a short demo of this. You know, from a material standpoint, it's just one of our materials, and if they say saturated, then you know that's one of our refrigerants that we have in the database. So this is R134A. The only real thing I have to do here is just make sure that when I'm in my scenario that I actually get my scenario environment reference at the right pressure. So that's the pressure that this fluid is going to be interacting. If it's looking at the scenario pressure, right? In this case, if I look at its material environment reference for the not using the environment, it's actually using its own. So that's the saturated pressure that I'm looking at. That's the only thing you have to make sure of is for whatever fluid I choose, if it's looking at the scenario environment, that I have the right pressure. If it's not, if it's using its own individual for the reference pressure, that we put that pressure in properly. That's the only hang-up I would typically see a user that wants to do the phase change go through. After that, we're entering in the flow rate, the temperature obviously, because it is a thermal problem, and then the quality. So if it's a quality of 0, that's right at that saturated phase. If it's a quality of 1, talking about going into superheat. So typically it's going to be entering in somewhere in between. And there you go. So that's materials and battery conditions. From a solving standpoint, you're just on the physics, just need to make sure you turn it on. So turn on quality, right? Because we're looking at the quality of the fluid as it goes through. So what does it look like in results? What kind of things can you look at? It's a ton of things here. The main thing that I would just kind of emphasize is that if you look at this graph here, you can see that it's coming in as a quality 0.5 saturated refrigerant, and it's actually exiting at a much lower density. That's because the quality is changing. It's becoming more vapor. If I quickly make a change, we can go ahead and look at that result here. So let's look at what is the quality. So scalar variable is how we track quality. So you can see again 0.5, and actually on this one, if I look at that, it's actually a quality of 1. That means it's actually driving into superheat. And if I wanted to see what that really means, look at the temperature. So it's going from the saturated vapor and starting to hit superheat right here and get out of that isothermal isotemperature phase where it's actually driving up in temperature as it goes into superheat. So you can actually accurately predict that where you couldn't do that in the past. And just as important, our pressure drop is now taking into account all these changes in density and everything where you're getting an accurate pressure drop as well. Hopefully that makes sense to everybody. It's physics that we haven't tackled before, and we're doing it in a way that there's very little extra effort on the user's part, but getting you the valuable information. So for somebody that's actually designing this, what they're going to try to avoid is what I was showing earlier, which is getting out of the isothermal stage, getting to where your heat transfer is going down, and they'll probably increase the flow rate in this case, or shorten the channels, one of the two, right? Anyway, that's
Heath, we did get a question on. Hey, Heath, we did get a question on how to define a custom phase change material. So maybe you want to show where those files are. It's not a straightforward process. I'll say that right now, but it is achievable.
So there is. I put it in here. I hid the slide because I thought I might get this question later on. So let me make this bigger. So this is what again, if you go into the material editor, what you would see for a typical fluid, right? One that actually exists. and you could actually pull from the thermodynamic tables that exist. So you would see ammonia, a few of the R1, a few of the refrigerant blends, and steam. Now, they're pointing to thermodynamic tables for density, viscosity, conductivity, specific heat. So not just like, they're actual thermodynamic tables. And where they're located is in your program data, Autodesk Simulation CFD 2015. If you're going to put in a custom blend, I would look at the format of these tables and just put in the properties for the fluid that you're going to use. And just make sure that they exist here. If you make a copy, it will automatically show up in this table file. Even if you're in software, you close and open this dialog box. If you've made a new one, it will show up. It will be refreshed. So without going into the details of modifying all the properties, but just you open up the tables that are in there, make a copy, and just put your properties in, and it will show up, and then you've got your new material.
So it seems like the questions are dying down a little bit. We'll hang out here for a few minutes and see if there's more questions, and we'll answer them directly. One thing I was going to do is actually make myself presenter before people start jumping off. I was going to show the results of the polls from earlier.
I'm interested. I didn't get to see them.
Exactly. So can you see this now, Heath?
Yes, I can.
So actually, I found these poll results very interesting. They're basically a perfect bell curve for the size of models most people run. It's definitely centered around 1 to 3 million elements, which is, in my opinion, a great place to be. You can still get good runtime for your simulations. Most everyone's using 2014, which is great. And a few people are still lingering in 2013. There's probably good reasons why they're still there for those few people. And the last question, a lot more this time around on more advanced users, as well as ones that have done a lot of projects but don't think they're they're power users yet. In previous Hangouts, we've had a lot more on the never open the software working through basic training models. So this type of Hangout definitely attracted our more seasoned vets. So just wanted to show that to everybody, and I'll pass this back to Heath just in case there's something else we want to show live.
Can you leave it there for just a second for me?
Yeah, sure.
So I just commented, I think what we have found, a lot of the reasons that people might stick on 2013 might have been due to some geometry import issues, and I didn't really highlight that for 2015, but we really worked hard on that as well. So we had gone through some architecture changes when going from 2013 to 2015 that caused some models not to come through. I would highly encourage guys to just test out 2015 on those same models they might have had issues with, because we're having a hard time finding models that don't come in at this point. So due to a concerted effort, just want to bring that up. So anyway, that's it. I saw that result.
Yeah. That's an interesting thing to pose, Steve. What else comes to mind for users that were still using 13 that may have been roadblocks for 2014?
Other than contractual issues, I don't see, maybe not having access, or, being in the middle of projects where they don't want to change revisions or versions of the software. I don't really see a reason. The only from a software standpoint reason that I've actually seen it was that geometry import issue. If there are others, I really would like to hear, because that means we're not addressing things, or that we've negatively impacted the software, which is something we totally try to avoid, obviously. I feel free for the guys that are in 2013 to reach out if there's a programmatic reason why they're staying.
Yep. So we're starting to get some more questions that are coming in. We have another one about enhancements for the HPC in 2015.
Yeah.
And clusters, things like that.
Yeah. So that's a topic that what we have addressed in HPC for 2015 is really the ability for the remote solve to be as robust as possible for workflows. We had some customers that had workflows that we didn't anticipate in the architecture that would actually cause our emote solve to basically fail. So you'd be solving and whatever the workflow is, shutting the computer off, getting off network, I don't know what it is, but and then to get the information back wasn't happening. So that was what you'll see in 2015, huge improvements there. If you're talking about scalability, that's something that's in development that we're working on. I can't really elaborate too much, but I'd be interested to see who sent those questions in. I might actually contact them directly, Royce.
Okay.
So.
Yeah, we got that here.
Cool.
And then another question, and this is always something that seems to change every year, but where do the announcements get posted regarding new versions, new service packs, other than the product website?
Right. So you guys can answer this as well. What we typically do is make the announcements on the forums. We do have in product through the communication center in the product, and as a matter of fact, we're about to put one out through the product where when you open it up, the communication center will say, hey, by the way, there's a new one. Going forward, there's something we've added to the software which will actually check for updates for you. And for all of Autodesk software, as a matter of fact, where if there is a service pack that comes out, it will inform you that there's a service pack and stuff like that. Without you checking, right? You can manually check for updates right now. But the other places that we typically make announcements are all of the Autodesk, simulation sites. Like if you go to the Facebook page, SimHub, you name it, we'll typically make those announcements. So there is an automated process that we send out information about new downloads being available, but it typically doesn't go to the end user. It typically goes to the contract manager. So that's why we make all these social media announcements in order to really get the word spread. If you've been a long-time customer, you should notice we can't really announce because of our public status the exact release dates, but you should notice a pretty consistent theme on dates, and it's usually about this time that we're sending out new versions of software.
We got one suggestion that came in, which you might find interesting. And currently in the software, we have the notification ability for sending out emails for on intervals or when the analysis finishes, things like that. It might be interesting to leverage that to allow customers to get notifications when there are new releases or updates as well. Maybe if there was a checkbox in that window saying notify when new software is available, might be another avenue to leverage.
Okay. Yeah, that's a good suggestion. I think what'll be, you'll start seeing that, and one of the things that we've even done is that when you install the software, there's another small application that will actually, it's even better than that, I think. If you have your computer on, it'll actually say, hey, there are updates to your software available, and that's something that you can disable, but if you leave it on, then the day that new software comes out, you'll see a little message in your taskbar saying, hey, by the way, CFD 2015 SP1 is out, or if you run Inventor, Service Pack 2 is out, or 2016 is out. You'll see those come through, and that's something new that we've introduced. And I think it's even more reliable than email, because emails change, but if you're running the software, your computer's going to come on. But yeah, I think that's great. We could add that as a benefit as well. So I think the guys will be pleased with our in-product communication, even when you don't have it on. So. Is there anything else that you see?
This is a very common, so this came in from one of our users, and I'll just address this directly. You're right that having the emails going right to the product manager or some company contact when sending out notifications through emails is typically bad. A lot of times that person's in purchasing or an IT personality, somebody like that, who really don't tell you when, as a user, that there's updates available. With the app manager that Heath just talked about, as well as with in-product notifications and what is available in social media, I think a lot of that will start to be less of an issue. So, I just wanted to get to that. So let's see how the new features come out in 2015 and see if it helps out or not.
Yeah. I think for the guys around 2014 and 2013, they'll probably still have the same questions, when's new software coming out and all of that. But anybody that goes to 2015 and beyond will get, like you said, it'll be hard to miss when new software is available as an end user. So I'm really looking forward to that because that's been a dilemma for us for a while. How do we contact the end user properly without being obtrusive into their work environment, basically?
Okay, at this point, I'll just give it another minute for people to ask questions, and if there are no more questions, then we'll end the Hangout a few minutes early. Just before people hop off, I just want to thank Heath for presenting here, and hopefully he will come back again in the future for us.
Hey, man, I had a great time. It's something I enjoy doing. If there's other topics that I can help out with, I typically actually watch these as an observer. So, in development, we try to stay in tune with the user base. That's what we really strive for, and I appreciate you having me on.
You're welcome. So if there are no more questions, I will end this meeting, and I just want to thank everybody for joining, and hopefully we'll have another Hangout within the next 3 to 4 weeks.